Chapter 6 is about exploring paired data. And in lesson 6.1, we're going to look at experiments using paired data. We're going to compare and contrast this to what we learned in chapter 4 about designing traditional experiments. For example, suppose that you wanted to design an experiment to see whether students can putt better with a traditional or short putter over an anchored or long putter. One way you could design an experiment to determine this is as follows. You could randomly assign all the members of your class to one of two groups, either a traditional or an anchored putter. So basically, you're splitting the class into two separate groups, and they may or may not be the same size depending on how many students are in your class. You could make sure that all members of the class putt under the same conditions, meaning they would be putting on the same green, using the same golf ball, holding the putter the same way, and so on. We would also want to measure then the distance each student's golf ball lands from the hole to determine which type of putter is better. So here we're looking for accuracy, where golf balls that land a shorter distance from the hole would be considered more accurate putts. Now, one problem with this design is that even with random assignment to the groups, the ability of the students in each group might not be the same. For instance, if the students who have greater golf ability are all assigned to the traditional putter group just by chance, this might make it seem that the traditional putter is better. Another problem for this is that there are variables for which we can't control. So, a better way to design this experiment would be to use paired data, and there would be two ways that we could do this. Number one, we could have all subjects in our experiment receive both treatments in a randomly determined order. What this would mean in our golf experiment is that we would have all the members of our class use both putters, but we would randomly determine that one group of students would use the long putter first and the other group would use the short putter first. That way, we would kind of negate the effects of having warm up time, where students that use the whichever putter they use second, they might use better because they've had a little bit of time to practice putting first. Another way to design an experiment with paired data is to take two measurements from each subject. Usually, this will involve one measurement before the treatment is administered and one measurement after the treatment is administered. And a before and after approach is not really appropriate for our putting experiment, but this would be something that you might use. Like, for example, in chapter 4, when you watch the video about the Would You Fall for That whiffed energy drink, they took before and after measurements in those cases. And that happens a lot in drug trials. Now, the advantage to these designs is that any uncontrolled variables should be operating equally on each treatment group, and the effects of the variables that we can't control or don't know about are balanced out. So, in each case, then, what you're going to really look at is calculating a mean difference to see if your treatment caused a response. So, as an example, we have some data here where we have a class of statistics students that's conducting the golf experiment, and they're doing it in the paired way. So, each student putts one golf ball with each type of putter from a spot 6 feet from the hole. So, that's a variable that we've controlled. We're making sure that each student is putting from the same distance. Now, the order in which the putters are used is randomly assigned for each student. So, one way that you could do that is you could have each student come up to the putting green and you could do something like flip a coin, for example. And if the coin lands showing heads, they would putt with a traditional putter first. And if it lands showing tails, they would putt with an anchored putter first. You could also put all the students' names in a hat, and then you could draw. And the first 7 students that are drawn would putt with a traditional putter first, then anchored, and then the other would do the reverse. However, you decide to randomly assign the treatments, we've got some data here that we're going to examine. So notice that we've got each student's number and we've got their measurements for the traditional and the anchored putter. So for student number 1, the distance that their golf ball landed from the hole with a traditional putter was 3 centimeters. With an anchored putter, it was 4 centimeters. And what we want to know then is the difference in those measurements. Now, the reason the difference is important is because you might have a student, for example, student number 1 seems to be a pretty good golfer. With both types of putters, their golf balls were only 3 or 4 centimeters from the hole. Now, look at student 5, for example. Student 5 doesn't seem to be as good a golfer, right? Their golf balls landed much farther from the hole. But what we're really interested in is the difference between the two types of putters. So, whether they're a good golfer or a bad golfer, both students were able to get the golf ball a little bit closer to the hole using the traditional putter. And so, what we really care about is how much closer to the hole was it, regardless of whether they're a good golfer or a bad golfer. So, we're going to subtract to find all those differences. And in each case, I'm doing traditional minus anchored. So, the top one minus the bottom one. You'll notice that in some cases we ended up with a negative difference, which indicates that the traditional putter was a little bit closer. In some, we had a positive distance, like student number 3. Here, they were closer with the anchored putter. And in a couple of cases, we actually ended up with a difference of 0. Now, a difference of 0 doesn't mean that they got a hole in one, although that did happen with student number 6. They were able to make their putts with both putters, but it means that their distance was equally far from the hole. So look at student 12, for example. With both putters, this golf ball ended up 6 centimeters from the hole for a difference of 0. That means it didn't matter which putter that student used, they still landed their golf ball 6 centimeters from the hole. Now we're going to make a dot plot of those differences. So I'll number my scale, and then I'll just make a quick dot plot there of only the differences. Now for part B, it asks, what does it mean if the difference for one of the students is positive? As we already mentioned, that means that their traditional putt was farther from the hole. And if the difference was negative, that means that their anchored putt was farther from the hole. We had some positives and some negatives. Now, part D, it says to calculate the mean difference. Now, we can do that a couple of different ways. One is that we can just add up all of those 14 differences, including the negative signs, and divide by 14. Another way that you can do that is to put those differences into list 1 in your calculator and then calculate the mean using the one variable stats function on your calculator. Either way, we come up with a mean difference of negative 8.57. And it says to mark that on the dot plot. So we'll go back to our dot plot. Negative 8.857 is right about there. And the fact that that mean difference is on the negative side is important to us, because when we end up with a negative difference, that means that the students were closer with the traditional putter. Or in other words, the anchored putt distance was farther away. So if we interpret that mean distance, we would say on average, students' anchored putts are farther from the hole than their traditional putts by 0.857 centimeters. So notice we're not including the negative sign in our interpretation. We're interpreting that negative by indicating which distance was farther from the hole. All right, let's look at a second example. Speed skating is a situation where races are run in pairs. That's just how the sport is set up. And you've probably seen speed skating in like the Winter Olympics. Two skaters start at the same time, one in the inner lane and one in the outer lane. Halfway through the race, they cross over, switching lanes so that each will have the same distance in each lane. And you may be familiar with why they do this already. If you think about a track and the way that it's set up, if you stayed in the outer lane the entire time, you would be skating a longer distance than the skater in the inner lane. So, to make sure that both skaters skate the same distance, they switch lanes halfway through. So, even though this seems fair, you suspect that there may be an advantage to starting in one lane as opposed to starting in the other. You design an experiment in which you use 17 pairs of skaters. The lane each skater starts in is randomly assigned, and each pair will race 1,500 meters. And what we've provided you with here are some data, which are the times given in seconds. So, for example, in skating pair number 1, the skater that started in the inner lane finished the race with a time of 125.64 seconds. The skater that finished or started in the outer lane finished the race with a time of 122.23 seconds. And so the difference, inner minus outer, there is 3.41 seconds. And remember, when you are measuring race times, a smaller time means that that racer won the race. So in skating pair number 1, the skater that started in the outer lane was the winner, and they won by 3.41 seconds. Again, notice we have some positive and some negative differences. And in this case, we gave you most of the differences. But let's just note in the margin here that this first row here indicates that the inner lane was the slower skater. The negative differences indicate that the inner lane was the faster skater. We didn't have any zeros in this case. There were no ties in the race, but in your notes there, section A, the first thing they want you to do is to complete the table. So notice in each case we're doing inner minus outer, so just be sure that you're subtracting in the right direction so that you get the correct sign on each of those differences. Now, part B is going to ask you some questions about the experiment. Part B asks, what is the explanatory variable in this experiment? Well, in this case, the starting lane is our explanatory variable, right? Whether they start in the inner or the outer lane. The response variable, you may remember, is what we measure at the end of the experiment. And what we're measuring is the time that is needed to race the 1,500 meters. Some variables that we could control in this experiment, well, obviously, we would want them to skate on the same track so that each pair is using the same track and skating under the same ice conditions and so on. We may want to dictate that the skaters have to use the same type of skates, although that might be a little bit more difficult to control because typically skaters have a pair of skates that they're very comfortable skating in. So that might be a questionable variable, but definitely we would want to have them skate on the same track on the same day. And then part E is asking, why does this experiment yield paired data? Well, we're taking two measurements from each race. We're taking inner and outer, and they're skating at the same time. So it's sort of a natural pairs setup that would lead us to analyzing paired data. Now, in this case, if we calculate the mean difference, it works out to be 0.499 seconds. And notice that that is a positive difference. So, how would we interpret that? We would say, on average, skaters that start in the inner lane are slower than skaters that start in the outer lane by 0.499 seconds. Now, we're not really sure whether that's a significant difference or not. For now, it seems pretty significant though, because 0.499 is basically half a second. And in a situation like the Olympics, a half a second is a really big difference. That concludes section 6.1. So please do the 6.1 homework in your assignment packet.